In this video, I'm going to show you how to model with exponential equations. So here's the first problem. A tree is growing. Each month, each of the tree's branches splits into 2 branches. Initially, there were 5 branches. How many branches are there after 3 months? Alright, so why don't we organize our work a little bit and write down how many months and how many branches. So initially, that's at 0 months because that's when we start. So 0 months. How many branches are there at 0 months? Well, there's just 5 branches. Okay, so how about the next month? After 1 month, how many branches are there? Well, it says that each month, each of the tree's branches splits into 2 branches. So to get the new number of branches, we have to multiply the previous number of branches, 5 branches, times 2. Then say another month passes and we're at 2 months. How many branches are there? Well, again, each of the tree's branches splits into 2 branches, so we're really just multiplying by 2 again. 5 times 2 times 2 again. And we can write that a little bit more compactly since we've got some multiplications by 2. Repeated multiplication is just exponentiation. So 5 times 2 to the power of 2, because we're multiplying 2 2's. Alright, let's do this one more time. We only want to go up to 3 months, so this will be the last round. 3 months. Again, we're multiplying by 2, because each branch is splitting into 2 branches. So we have 5 times 2 times 2 times another 2. That's how many branches we have. And putting that into exponent notation, this is just 5 times 2 to the third, because 3 2's. And this is our stopping point because we wanted to find how many branches after 3 months. We've got 3 months here, so we really just have to evaluate this computation here. 5 times 2 to the third. Well, 2 to the third is 2 times 2 times 2, and 2 times 2 is 4, then times 2 again is 8. So this is really just 5 times 8. And 5 times 8, we know, is 40. So there we go. How many branches after 3 months? 40 branches. Here's another problem. A picture becomes worn over time. Initially, all 2048 pixels in the picture were intact. However, after 10 years, only half of the pixels are intact. If this trend continues, how many pixels will be intact after 50 years? Why don't we set this up in a manner similar to the previous problem? So initially, we're at 0 years. And at 0 years, all 2048 pixels are intact. So 0 years, 2048 pixels. Okay, then after 10 years, so 10 years is the next data point here. After 10 years, how many pixels are intact? Well, only half of them. So to get the new number of pixels, only half, we have to multiply the previous number, 2048, by a half. Okay, so now we want to continue this trend, and by the trend continuing, that just means we keep on multiplying by a half. The number of pixels keeps on halving every 10 years. So our next data point then should be 10 years after 10 years, which is 20 years. And the number of pixels at 20 years should be a half of the previous number. So 2048 times a half again, which, as we saw previously, that's just a half squared. So the next data point would be 30 years then. Go forward another 10 years, and we multiply by a half again. So 2048 times a half times a half times a half, so times a half to the third pixels. You can kind of see a pattern here. 10 years is a half to the first power, 20 years is a half to the second power, 30 years a half to the third power. So 40 years will clearly be 2048 times a half to the fourth power. All right, so we want it to go up to 50 years, so just one more row to do. 50 years will, of course, be 2048 times a half to the 5th power. Great, so that's where we want it to stop after 50 years. So now we just need to perform this computation here. And let's do that to the side. 2048 times a half to the 5th. First of all, what is a half to the 5th? Well, a half squared is a 4th. Then a half to the 3rd power is a half of that, so an 8th. And then a half of that is 1/16th, so a half of 1/16th is 1/32. So we really have 2048 times 1/32, which is the same thing as 2048 divided by 32. So we can just set up a long division here. 32 goes into 2048 how many times? Let's go ahead and compute this. So 32 goes into 2 0 times, 20 0 times, 204 it goes into several times. And how many times is that? Well, maybe think 32 is pretty close to 30 and 204 is pretty close to 200. How many times does 30 go into 200? 7 is close. 7 times 30 would be 210, but that's a little bit too much. So let's try 6. Let's do 32 times 6. 32 times 6, 6 times 2 is 12, and then 6 times 3 is 18, plus 1 is 19. 192. Yeah, we can't fit another 32 in because we'd go over 204, so 6 is our number here. 32 times 6 is 192. Now we just go ahead and subtract. 4 minus 2 is 2. 0 minus 9, so cancel this 2 to 1, carry the 1 over here. 10. 10 minus 9 is 1. So we've got 12 left over. Now bring down the 8 here. 32 goes into 128 how many times? Well, again, think 32 is pretty close to 30. 128 is pretty close to 130. How many times does 30 go into 130? Well, 30 times 4 is 120, and we can't fit it anymore. So that's a good indicator that our next number will be around 4. Why don't we check 4? 32 times 4. What does that equal? 4 times 2 is 8. 4 times 3 is 12. There it is, 128. So 32 times 4 is 128. There we go. Subtract, no remainder, and there we have it, 64. So there we go. This simplifies to 64 pixels are left after 50 years. Here's a final example. A small town is improving its sanitary practices and the number of recorded illnesses is decreasing by 2/3 every year. If there were 243 illnesses in 2016, then in what year will the town expect only 3 illnesses? Let's draw this out again like we have with the previous problems. So first of all, in 2016, there were 243 illnesses. Okay, then how about the next year, in 2017? How many illnesses? Well, we start with the amount in 2016, which was 243, but then we're decreasing by 2/3 every year. Now, decreasing by 2/3 every year, that means every year is 1/3 of previous year, which really means we just multiply by 1/3. So 243 times 1/3 will be the number of illnesses for 2017. Now we see where this is going, so 2018 we'll just have to multiply by 1/3 again, so that'll be 243 times 1/3 times 1/3, so times 1/3 squared. So the general trend is really that T years after 2016, the amount of illnesses is 243 times 1/3 to the T. 2017 is 1 year after 2016, 2018 is 2 years after 2016. So this is our general formula that tells us how many illnesses T years after 2016. Now we want to find in what year will the town expect only 3 illnesses. So what we can do is we can set this expression equal to 3, solve for t, and then use that to figure out what year it is. So let's do that. 243 times a third to the t has to equal 3 illnesses for the t that we're interested in. Let's go ahead and simplify this equation. So we want to get the exponentiated expression by itself on one side, so let's divide by that 243 on both sides over 243, and then that cancels out here and we just have 1/3 to the t equals 3 over 243. And the sum of digits here, 2 plus 4 plus 3, that's 9, which is divisible by 3, so we know that 243 is divisible by 3, and therefore this fraction can be simplified. So 3 times what makes 243? Well, 3 times 80 makes 240, so 3 times 81 makes 243. So this fraction can be simplified to 1 over 81. Let's continue simplifying. So 1/3 to the t, that's 1 to the t over 3 to the t, and 1 to the t is always 1, so just 1 over 3 to the t. So 1 over 3 to the t is equal to 1 over 81, and then flipping both fractions, we see that 3 to the t has to be equal to 81. Now 81 is just 9 times 9, and 9 is just 3 times 3, then the other 9 is again just times 3 times 3, so 81 is 3 to the 4th. So we have 3 to the t equals 3 to the 4th. That makes it clear that t equals 4. So we have that 4 years after 2016, there would only be 3 illnesses. And 4 years after 2016 is, of course, 2020. So that's the year that the town should expect only 3 illnesses. Now we know how to model some real-life situations with exponential equations. And in the future, we'll continue learning about exponential functions, including how to graph them.